the frequency is low and the energy is low. For shorter wavelengths, there is a higher frequency. The frequency is higher energy. An example of high energy waves such as ultraviolet, gamma rays, X-ray, and example of low energy, low frequency is the infrared, the radio frequency, and also the very low radio frequency waves. There is a formula that correlates the frequency with the wave, with the wavelengths. C, the speed of light, equal the frequency times the wavelength. So it is essentially, since the speed of light is fixed, then there is an inversely relation between the frequency and the wavelength. This is example. If you know the wavelengths, you can use the formula to get the frequency. Here, the blue light, for example, 400 nanometer. You need to use the speed of light divided by the wavelength, and then you can get the frequency in hertz. When the photon interact with matter, the electromagnetic radiation can exhibit particle-like behavior. It's called photon or quanta. The photons are bundles of energy. So we can describe the electromagnetic radiation in terms of the photon energy using the Planck formula. Energy equal Planck's constant times the frequency. So as we can see from the formula, that the amount of energy carried by the photon will depend on the frequency of the radiation. The unit of the energy, we know it's joule, but there is another practical unit. It's called electron volt. 1 electron volt is defined as the energy acquired by an electron as it traverses an electrical potential difference of 1 volt in vacuum. So we have we can have mega electron volt, 1 million electron volt, and also a giga electron volt, and so on. And these are the electron volt in joule seconds, and also the max constant in terms of electron volt second and kilo electron volt second. So we said that as per the photon model, electron is equal to the Planck constant times the frequency. We can also use the formula for the wave from the wave model and join it together to get the electron will be equal the Max Planck constant times the speed of light over the wavelength. So this formula will give me the energy in terms of the wavelength. Now we move to the atom. We know the atom consists of the nucleus. The nucleus consists of protons and neutrons, and it is surrounded by orbiting electron at the atomic levels around the nucleus. This is the Bohr model. And here we can see that the neutron mass is slightly higher than the proton mass. Of course, the charge is different. The proton is a positive charge, and the electron a negative charge, and the neutron is neutral. So the charge is 0. Definition of the atomic number. This is important. So as we can see, the atomic number affects many of the parameters that we will see in diagnostic radiology. The atomic number defined as the number of protons in the nucleus, and the mass number is the total of the atomic number, the number of protons, and in the number of neutrons. For example, here we have the carbon atom. The number of neutrons, or the Z number, is 6, and the number of neutron 8. So their total is the mass number 14. We talked about the electron that's orbiting around the nucleus in the atomic levels. Each electron occupies a discrete energy, so each electron has a certain energy around the nucleus. It's called electron shell. So we have K shell, L shell. For example, number 1 is the K shell, very famous. The L shell, the second one, and the M, third, and so on. There is a limit to how many electrons occupied by each shell, to n squared. For example, N1 in the K shell, the maximum number is 2. For the N2, the maximum number is 8 electrons, and so on. The outer electron shell is called the valence shell. It determines the chemical properties of the element. For example, here the tungsten atom, it has 74 protons, so the Z number is 74, and it has 110 neutrons and 74 electrons. So the atom is neutral, because the total number of proton equal the total number of electrons, so the net charge is 0. So the neutral atom, it has a net charge of 0, so it is stable, or we call it non-ionized, because it's electrically neutral. Photon or particulate form, as we can see, such as beta or alpha, when interact with sufficient energy equal or more than the binding energy, it can ionize one of the electron and remove it from the atomic shell, and then it will produce ionized atoms, and we call it ionized. Usually, electron radiation with wavelength shorter than 100 nanometers carries sufficient energy per photon and can remove electron from the outer atomic shells. Therefore, the electromagnetic radiation of higher frequency than the near ultraviolet region of the spectrum carries sufficient energy per photon to remove bound electrons from the atomic shell and ionize the atom and the molecule. The electromagnetic radiation with energy below the far ultraviolet region, such as the visible light, infrared, radio, TV, are called, as we mentioned, non-ionizing radiation. So only high energy ultraviolet and above can ionize the atom. So when the atom loses one of the electrons, it is not anymore a neutral atom, and we call it an ionized atom. When the electron also, the atom has extra electron, it's called also ionized. So either it loses electrons or gain extra electron, and the net charge is not zero, then we call it also ionized. So the ionized atom is not electrically neutral, but carry a charge equal in magnitude to the difference between the number of electrons and the number of protons. But atom cannot be ionized by addition or subtraction of protons, such such action will change the type of atom. Generally, ions can interact with living tissue. That's why ions are important in the science of radiation biology, because they interact with the living tissue to produce biological damage. As we mentioned, the radiation in the portion of the spectrum, ultraviolet, X-ray, gamma ray, sufficient energy, is called ionizing radiation. Now, the issue of are there a certain energy where we can say this energy is ionized radiation or non-ionized? Actually, the threshold energy for ionization depends on the type of matter. For example, the minimum energy necessary to remove electron from water molecule H2O is 12.6 electron volt. But for C2H6 is 9.3. It's even lower. So again, the ionizing energy will depend on the matter itself. But the rule here is that whenever the energy can ionize the matter, it's called ionizing energy or radiation. Of course, a major source of ionizing radiation is nuclear transformation with either with radioactive material or in accelerators. Now we talk about the particulates. It is atomic or subatomic particle mass in motion, carrying energy in the form of kinetic energy. Example of that, a proton, which is the nucleus of hydrogen, H plus atom. Also, another example, electrons, which are ejected from the atom orbits, has a negative charge. Electrons are also emitted by the nuclei, some radioactive atoms. In this case, we call it beta particle. So we have here an example of proton and electron. We have also other type of particulates, such as alpha and positron and neutron, as we will see. The alpha particle consists of 2 protons and 2 neutrons. So it has a +2 charge, and it is identical to the nucleus of helium atom. Alpha particles are emitted by certain naturally occurring radioactive materials such as uranium, thorium, and radium. Following such emission, the alpha particles will acquire 2 electrons from the surrounding medium and become a neutral helium atom. Another example of particulate radiation, positrons, which is in nuclear medicine. As we will see, the positrons are positively charged electrons, beta plus we call it, and are emitted from some nuclei during radioactive decay. The last one is neutron. It is uncharged nuclear particle that has a mass, as we said, slightly greater than the proton. And neutrons are released by nuclear fission and are used for radionuclide production. Now we talk about the mass energy equivalence between mass and energy. In any reaction, the sum of the mass and energy must be conserved. We know that from classical physics. There are 2 separate conservation laws, one for mass and one for energy. However, in modern physics, Einstein showed that these 2 conservation laws are valid only for objects moving at low speeds. Einstein actually concluded in his theory, the theory of relativity, that the mass and energy are interchangeable at the speed associated with some nuclear processes that approach the speed of light. The concept of Einstein theory of relativity is that mass is a form of energy, or in other words, mass and energy are equivalent, and the 2 are related according to the famous expression mc squared, where E is the energy equivalent to mass at rest, and C is the speed of light in vacuum. An example of that is the electron mass. We can change, using the Einstein formula, we change the electron mass to energy, and we can see here that the electron mass is 0.511 MeV at rest. We'll talk also about the Avogadro number. It's equal to 6.022 10 to the power 23. I think you're all familiar with that. So we will use that to calculate the mass. The mass on the atomic scale is measured in atomic mass units, AMU. It's defined to be 1/12 of the mass of the carbon atom. So we can change the mass for proton, neutron, electron into atomic mass unit, which is the unit used for example, in the nuclear physics. It can be shown from the atomic weight of carbon. We can calculate the mass of one carbon atom to be 1.9927 10 to the minus 23 gram, and using the AMU definition, and we can change it to the NC square. We can change it to energy. and we can find that 1 AMU equals 931.5 MeV. So this is another way of demonstrating the mass in terms of energy. Now we talk about the binding energy and the energy levels. These concepts are important when we talk about the X-ray tube, and we understand the basic principles of the production of X-ray. So we need to focus on the binding energy and energy levels. So the electron binding energy is the energy required to remove an electron completely from the atom. The binding energies are a negative because it's binding, so it is negative, with increasing magnitude for electrons in shells closer to the nucleus. So as we come close to the nucleus, we can see here that the binding energy increases this way. For an electron to become ionized, the energy transferred to it from a photon or particulate form of ionizing radiation must be at least equal or exceed the magnitude of the electron binding energy. We have example here. For example, the K shell for the tungsten, 69.5 electron volt. We need at least an energy of 69.5 or greater than that in order to dislodge the electron from the atom. Also, as you notice, that the binding energy of electrons in a particular orbit increases with the number of protons in the nucleus or the atomic number. So since the atomic number for tungsten is higher than the hydrogen, you can see that the binding energy also is much higher. So here, as we mentioned, that for the tungsten, the Z number is 74. So it's much, the K shell electron is much more tightly bound than the K shell of the hydrogen. And the energy required to move an electron from the innermost electron orbit, the K shell, to the next one, the L shell, is the difference between the binding energy of the two orbits, and we call that the transition energy. So for we subtract the binding energy for the K and L for the hydrogen and tungsten, we can see here that the transition energy for tungsten is much higher. And we will have more about the electron binding energy in the coming presentation. So now we move to the second presentation. We talk about the interaction of radiation with matter. The objective of this presentation is we will describe the types of radiation, electromagnetic and particulate, the particle interaction with matter, excitation, ionization, and radiative, and also the photon or the X-ray interaction with matter. We will talk about the Rayleigh, Compton, scattering, photoelectric, and pair production. And then we will describe the energy dependence of these interactions. And we'll describe and calculate the various quantitative parameters used to characterize X-ray attenuation. Also, we will differentiate between the radiographic exposure, absorbed dose, and equivalent dose, and also we will use the correct radiological units. So the definition of radiation simply is the propagation of energy through space or matter. It can be either, as we mentioned in the previous presentation, either electromagnetic radiation, such as visible light, radio waves, X-rays, gamma rays, or particulate radiation, such as electrons, or neutrons or photons. The electromagnetic radiation propagates as a pair of electric and magnetic fields. We talked about the wave characteristic, the c, speed of light, the wavelength, and the frequency. All that we reviewed. C is constant, and then we mentioned that the frequency is inversely proportional to the wavelength. We talked also about the particulate radiation. When the interaction with matter, the electromagnetic radiation can exhibit particle-like behavior with a bundle of energy nodes and known as photons, which is defined by Planck constant, and it also can be described in terms of frequency or in the wavelength. And as we mentioned that the wavelength measured in angstroms or nanometers. And angstrom equal 10 to the power minus 10. And also we mentioned the electron volt, which is used in medical imaging, and also the MEV. The most significant charged particles are alpha particle, electron, positron, protons, neutrons. For the electromagnetic radiation, except for nuclear medicine, the electromagnetic radiation required also interact via absorption, scatter with tissue it penetrates. However, in nuclear medicine, the radioactive agents are injected or ingested, and the metabolic or physiologic interaction of the agent give rise to the information in the images. First, we talk about the particulate charged particles, as we mentioned, such as electrons, how the electrons or the positrons interact with matter. And then we will talk about the photons, how the photons interact with matter. But now we will start by the charged particles or the energetic charged particles. They are actually interact via the electrical forces. Since they are charged particles, so the influence of the electric force is the one that affects the matter that it interacts with. It will lose kinetic energy through excitation, ionization, or radiative losses. First, the excitation is the transfer of some of the incident particles' energy to electrons in absorbing material, promoting them to higher electron orbits. So when an electron or positron interact with the atom, the electron will move or excite to a higher level, and then return again, emitting electromagnetic radiation, and we call that excitation. So this is the first way of interaction between the charged particle and matter. So the energy is not sufficient enough to ionize the atom. So it is a lower energy that only excites the electron to another orbit, and then it return again, and we call that excitation. The other type of interaction is ionization, where the energy of the charged particle or particulate is sufficient enough to is higher than the binding energy of the electron, and in that case, the electron is ejected from the atom, and the atom is ionized, and we call that ionization. As a result, we will have an ion pair formed consisting of the ejected electron and the positively charged atom. Sometimes, if the electrons that have enough kinetic energy, they even further produce more ionization, and we call that secondary ionization. Or delta rays. It's called some text delta rays, additional or secondary radiation, because the coming charged particle has very high energy. Generally, approximately 70% of electron energy deposition leads to non-ionizing excitation. So most of the interaction of electron with matter is excitation only, without ionization. Now we define the specific ionization. It's the number of primary and secondary ion pairs produced per unit length of charged particle. It's called specific ionization, and it's measured per millimeter, ion pair per millimeter. The specific ionization increases as the particle charge increases and decreases as the velocity of the incident particle increases. So, for example, for alpha, it can reach as high as 7,000 ampere per millimeter. So the specific ionization is higher for alpha. For the electron, it's in the range 50 to 100 ampere per millimeter in air. Now we define the LAT, or the linear energy transfer. Actually, the linear energy transfer is important in radiation biology. It is the amount of energy deposited per unit length. And usually it is given in electron volt per centimeter. It is defined as the product of the specific ionization and the energy deposited per ion pair, or the energy needed per each to produce one ion pair. It is proportional to the charge of the particle and also the kinetic energy of the charged particle. The LAT describes the energy, the position, density, which largely determine the biological consequences of the radiation exposure. Example of high LET radiation, such as alpha and protons. Low LET, such as electrons, beta particle, positrons, X-ray, or gamma rays. High LAT, of course, they have more damage to the biological tissue when compared to low LAT. We talked about the excitation and ionization. Now we talk about the third type of interaction between charged particles and matter, which is the radiative interaction, or in Germany, Primstrahlung radiation. When a charged particle or electron interact or come close to an atom, a nucleus, the electron negative charge and the nucleus is positive, so it will be attracted by the nucleus, and this will decelerate the energy of the speed of electron, and it causes to emit electromagnetic radiation called Primstrahlung radiation, or breaking radiation. So when the electrons come close to a nucleus, they are decelerated in speed, and as a result of that, because of the physics laws, conservation of energy, it will emit photons or Primstrahlung X-ray, and this energy loss is responsible for the majority of the X-ray produced by the X-ray tube, as we will see when we talk about the X-ray tube. The probability of Primstrahlung emission is according to the Z number of the absorber, the square of the atomic number. So as the atomic number of the absorber increases, the probability for Primstrahlung increases. The ratio of electron energy loss due to Primstrahlung when compared to excitation and ionization can be calculated using this formula. the kinetic energy multiplied by the Z number over 820. So for 100 keV electron and using tungsten as a target, the tungsten has a high Z number, 74. If we use the formula, we will see that only 1% will be Bremstein radiation. So the emission by Bremstein is a low probability compared to excitation and ionization. Now we talk about the other type of radiation, or other than the particulate radiation. We talk about the electromagnetic radiation, such as X-rays and gamma rays, and how they interact with matter. There are several ways for the X-ray and gamma ray to be absorbed or scattered by matter. There are 4 major interactions are of important to diagnostic radiology and nuclear medicine, each characterized by the probability of interaction. The Rayleigh or classical, sometimes called coherent scattering. The second type, Compton scattering. The third is photoelectric effect. And the fourth one, the pair production. And we will talk about each one of these interactions separately. But these are the 4 types of interaction between the photons and matter. First, the coherent scattering or Rayleigh scattering. When the incident photon interact with the atom, it will only change the direction to scatter without losing any energy, and we call that coherent scattering. So no ionization take place with the matter. The photon is only scattered in different direction. No loss of energy also. But this type of interaction only occur at very low energy diagnostic X-ray, and we find that in mammography because we are setting the tube, the X-ray tube at low kV, around 28. So we are dealing with low energy X-ray. So this type is usually found in mammography. The probability is between 5 to 13%. The other type is the Compton scattering. The Compton scattering simply is the photon will interact with the one of the outer shell electrons, and usually the outer shell electron are very weak. It has very low binding energy and easy to dislodge from the atom. So the photon will lose some of the energy to the outer shell electron, which will be ejected from the atom, and the photon will change the direction and lose some of its energy. And we call this angle the angle of deflection, or the angle of Compton scattering. The Compton is a dominant interaction with soft tissue in the diagnostic range between 26 keV up to 30 MeV. So this is the main interaction with this range. Most of the interaction is Compton scattering. As we mentioned, that it occurs between the photon and the free outer shell electron. the energy of the photon is much higher than the binding energy of the outer shell. The binding energy is very small and can be ignored. The probability of Compton interaction is proportional to the material density itself. So the material density is the one affects the probability of Compton scattering. The maximum energy transfer to electron is at 180 degree backscatter, which means that the photon return back, and we call that backscattering. This is the maximum energy transfer to the atom. Also, the maximum energy to scatter photon is 511 keV at 90 degrees. So at 90 degrees, the maximum energy will not exceed 511 keV. This is the formula how to calculate the energy of the scattered photon by Compton using the angle of scattering. The Compton scattering, also called inelastic scattering, now as the incident photon energy increases, both the scattered photon and the electron are scattered more towards the forward direction. So for a given scattering angle, the fraction of energy transferred to the scattered photon decreases. At low diagnostic X-ray energy, the majority of the incident photon energy is transferred to the scattered photon, which, if detected by image receptor, would reduce the contrast. So as we can see, as the energy increases of the photon, we can see here that most of the scattering is at the lower scattering angle, and the direction will be mostly to the forward direction. The third type of interaction between photons and matter is the photoelectric effect. Here, as with the Compton, we said that the interaction with the outer shell electron. Here, the interaction with the inner shell, very strong binded energy inner shell, and the photon will interact, will be absorbed completely by the electron, and then ejected. So there is no scattering at all. Compared to Compton, the photon is deflected and scattered. Here, the photon is completely absorbed by the inner shell electron, and the electron is then ejected. And the energy of the ejected electron is the difference between the energy of the incident photon and the binding energy of the electron. So with photoelectric effect, the photon is totally absorbed. This is important for the image quality. That's why with photoelectric interaction, the image quality is better because it will not produce any scattered photons. The photon is absorbed completely, and then the electron is ejected, and there will be a hole. There will be empty space or empty hole in the K shell, which will be then filled by an outer higher energy electron. The electron, when fulfill that vacancy, an electromagnetic radiation is ejected, and we call that discrete or characteristic X-ray. It has as we mentioned, that the incident photon will be absorbed completely by the electron inside the atom. The electron is ejected. There will be a hole, and then that hole is a higher level electron will come to fulfill that hole, and then electromagnetic radiation is ejected. We call it characteristic radiation. It has a unique energy to the target itself. So the characteristic X-ray is a result of the photoelectric effect, but also there is another interaction. We call it Auger electron. We will not. It is not the Auger electron is not important as the characteristic X-ray. We have a negative ion photoelectron and a positive ion, which is the atom, a product of the photoelectric effect. Now the probability of photoelectric absorption is proportional to the Z number to the power 3 over the electron to the power 3, which means whenever the Z number higher for the target, the probability for the photoelectric effect increases, and also at a lower energy. For higher energies, the photoelectric interaction become less important. So due to the absorption of the incident X-ray without scatter, maximum subject contrast will arise with the photoelectric effect interaction. It's explain why the contrast are reduced for higher energy X-ray are used in the imaging process. If the energy, the photon energy double, the probability of photoelectric interaction is decreased by a factor of 8. That's why the photoelectric is only below the 26 keV range. If the energy is higher than 26, then the Compton scattering will be will be with higher probability. So the increased probability of photoelectric absorption just above the binding energy of the inner shell cause will cause discontinuity in the attenuation profile. So here, to compare the profile for the barium and iodine, both of them are of higher Z number when compared to tissue. We can see here that there is an increase in the attenuation for both material because of the K-edge or because of the photoelectric effect will start at the binding energy for the K shell. So the edges become significant factor for higher Z material as the binding energy are in the diagnostic energy range. That's why we use contrast agents such as barium and iodine. Rare earth material used for intensifying screens in the screen film because of their K shell or the edge energy. Increased absorption probability improve the subject contrast and quantum detective efficiency. So at photon energy below 50 keV, the photoelectric effect plays an important role in imaging soft tissue, amplifying small differences in tissues and slightly different Z number, so improving the subject contrast, especially in mammography. Generally, the photoelectric process dominates when lower energy photons interact with high Z number. This is the primary mode of interaction of X-ray with screen, phosphors, contrast materials, and bone. Compton scattering, on the other hand, will dominate at most photon energy in material of lower atomic numbers such as tissue and air. The fourth type of interaction between photons and matter is the pair production. The pair production will start at very high energy, above 1.02 MeV. So at such energy level, when the photon come closer to the nucleus, it will eject create two particulates, beta particle and positron. And the positron, when facing electron, it will annihilate and eject 2.511 MeV photons. So this is the outcome. We have two photons, the outcome of the pair production interaction. The positron or the beta plus particle, when encounter an electron of the opposite charge, it will create two 511 keV photons separated at an angle of 180. This is the basis for the PET imaging. The outcome, as we said, that we have two photons. Actually, pair production is not important in diagnostic X-ray imaging because of the high energy threshold requirement for this to occur. above 1.02 MeV. Now we talked about the type of interaction. We talked about attenuation of X-ray and gamma ray, or photons in general. The definition of attenuation is the removal of photons from a beam of X-ray or gamma rays as it passes through the metal. Attenuation is caused by both absorption and scattering of the primary photons. We define the linear attenuation coefficient, or mu, as the fraction of photon removed from a monoenergetic beam of X-ray and gamma ray. We mean by monoenergetic the beam that has the same energy. The photons, they have the same energy per unit thickness of the material. For a monoenergetic beam of photons incident upon either thick or thin slabs of material, an exponential relationship, we can use this formula. This is the number of incident photons before the shield and the number of photons after the shield. And mu is the linear attenuation coefficient, and x is the thickness of the material or the shield. Now we define the half-value layer, which is important in diagnostic radiology. The half-value layer is the thickness of material required to reduce the intensity of the incident beam by half. Which means if we have a beam of a certain intensity, the thickness of material required to reduce the intensity to 50%, we call that the half-value layer. And the half-value layer is defined as ln2 over the linear attenuation coefficient. Usually, the unit of half-value layer is expressed in millimeter of aluminum. Usually, aluminum is used as the definition for the half-value layer for diagnostic X-ray beams. And it is a measure of the average energy of the photons in the beam. So when we say the half-value layer, this beam has a higher half-value layer. That means it has a higher average energy or higher quality. It can be also expressed in to the power n, half to the power n, where n is the number of half-value layer. The half-value layer is a function of photon energy. So whenever the energy increases, the half-value layer of the beam increases. The geometry also affects the half-value layer, and also the attenuating material will affect the half-value layer of the incident beam. Also, in this diagnostic radiology, we use the unit of kerma. You will notice in some of the units they use the kerma unit. The kerma is defined as the kinetic energy released in matter. It's defined as the kinetic energy transferred to a charged particle by indirectly ionizing radiation per mass matter. So we have photons, which are such as X-ray or gamma ray. transferring the energy to charged particles such as electron. The air kerma is the total kinetic energy transferred to the charged particle, and the unit is joule per kilogram, or we call it gray. Also, we absorb dose is used when we talk about diagnostic beams. The absorbed dose is the energy deposited by ionizing radiation per unit mass of material in joule per kilogram, which is also the unit of gray. 1 gray equal 1 joule per kilogram. There was a traditional unit called the rad. 100 rad is equal to 1 gray. So the rad is about 10 milligray. The exposure defined as the amount of electrical charge produced by ionizing radiation per mass of air. So the charge coulomb per kilogram. This is the definition of exposure. But also there is another unit, the Rontgen, which is defined in coulomb per kilogram. It's used frequently when we talk about exposure, or the milli Rontgen. The exposure can be measured using air-filled ionization chamber or servimeter. This is example of ionization chamber. So we can measure the output intensity of X-ray tube in terms of unit of millirontgen per unit mass, or the multiplication of the current in milliampere with the exposure time. The dose in gray can be converted to exposure using the Rontgen to gray conversion factor. In air, it's about 0.876, and for radiation protection purposes, they equal it, they round it to 1 for air. So if you have a unit of Rontgen, if you measure in Rontgen the X-ray beam exposure, you can use this formula to change it to dose in air. Usually, the exposure is nearly proportional to dose in soft tissue over the diagnostic radiology range. So, whenever you increase the exposure, also the dose is increased. However, for bone, the Rontgen to rad conversion approaches 4. So it is not, we cannot round it to 1, as we can see here for soft tissue and water. They are almost the same. For bone, it's different. So the exposure is not equal to the dose for the case of war. Also, the equivalent dose is used, the unit of equivalent dose in diagnostic radiology is measured in, the unit is sievert or SV. In general, for high LET radiation, such as alpha particle, proton, are more damaging than low LET, as we mentioned. So there are different radiation weighting factors. The equivalent dose is defined as the radiation weighting factors multiplied by the dose. There are examples here for the X-ray, gamma ray. The weighting factor is about 1. For the proton, it's between 5 to 10. And for neutron, also between 5 to 20. So it's different. Different type of radiation will have more different damaging ability to biological tissue. For alpha, for example, is 20. So the unit of equivalent dose in sievert, it will take into account the different damaging capabilities of different type of radiation. The old unit, REM, is equal to 10 millisievert. Also, the effective dose is used in diagnostic radiology because not all tissue they have the equal radio sensitivity. So as you can see here, different type of tissue, they have different tissue weighting factor, which means that they are different in their radio sensitivity to radiation. So the effective dose will take into account the radio sensitivity of each radiated organs. So after we calculate the equivalent dose for each organ, then we can multiply that with the tissue weighting factor to get the effective dose, which will take into account the radio sensitivity of each organ. So in summary, we said there are different type of units used. First, the exposure. It's used to compare the assessment of equipment performance. If you have different X-ray units, different output of radiation, so we use the exposure to compare. The unit is Rontgen. We have the absorbed dose. It's used to calculate the organ dose, such as dose to uterus, for example, and the unit is rad or gray. Also, we talked about the KERMA and the equivalent dose and the effective dose, which is used to compare the risk of stochastic effects, to compare between different imaging protocols. Take into account, as we said, the radio sensitivity of the organs, and the unit is sievert, and the old unit is red. So uh, uh, we'll take a break, a short break for 10 minutes, where we talk about the X-ray output and X-ray tube. So we will be back at inshallah about 9:30. Okay, we move to the next presentation, the X-ray production and tube output. The X-ray was discovered in 1895 by Rontgen. Rontgen was doing experiment with a Crook tube, which is a tube that uses electron beams, and then he by chance discovered that there was a fluorescent material, and that material glue in the dark, and he concluded that there is a radiation. He called it X radiation, which means that unknown radiation. That's why they call it X-rays. And the first radiograph was his wife's hand, and it was in December 22, 1895. So basically, the production of X-ray, we have a target and a beam of electrons hitting the target, and the X-ray are reduced. So this is the basic picture of X-ray production. So we have an electron source. We have the target, which is the anode, and we have evacuated path for electron to travel through. We call it the X-ray tube insert. And we have the external energy source to accelerate the electrons by a generator, to accelerate electrons so that it will hit the target and the X-ray are produced. First, we'll talk about the electron interaction with the anode or the target. As a result of the interaction between the electrons and the target, the heat is generated. Most of the interaction will be in the form of heat. The kinetic energy of the electron deposit its energy in the form of heat. So these are collision-like interaction with the atom, where the kinetic energy is of the electrons are less than the binding energy. So it will result in the emission of infrared radiation. This will reduce the heat. It's account for the majority of the interaction with the target. Almost 99% of the interaction will be in the form of heat. Only 1% of the electron interaction will result in X-ray production. And that 1% is in the form of Bremsstrahlung radiation. We talked about in the previous presentations. Bremsstrahlung radiation or braking radiation. It's a continuous energy spectrum. Coulomb interactions. The electrons are decelerated, and the Bremsstrahlung radiation will be produced. The other type of X-ray, we call it the characteristic X-ray, discrete energies. Whereas the Bremsstrahlung is continuous energy, the characteristic is discrete energies. So the incident electron collision with the orbital electron in the shell has energy enough to dislodge or eject the electron from the shell. This is the only way we can have characteristic X-ray. So the energy should be at least equal to the binding energy of the shell, so that we will have characteristic X-ray. We said that most of the interaction between the electrons and the target will result in a heat production in the anode. It increases directly with the increasing X-ray tube current. So if you increase the X-ray current, if you double the current, you will double the heat. So using more current, that's mean more heat to the X-ray tube. Also, the kV itself, if we increase the kV, it will also increase the heat also. So the kV also has an effect on the heat of the X-ray tube. We talked about the X-ray production. We said that two types of X-ray are produced: the Bremen-Stahling radiation characteristic. So for the Bremen-Stahling process, the cathode, as we said, the role of the cathode is to produce the electrons, and the anode it will be the target. The anode is positive to attract electrons. A large potential difference, KVB potential, is applied across the two electrodes in an evacuated envelope or the X-ray insert. So when the cathode, the electron released from the cathode will gain kinetic energy because of the applied voltage, and they will be accelerated towards the anode. The energy of the electron is expressed in kilo electron volt. We said that there are different units for energy. One of them is the electron volt or the kilo electron volt, 10 to the power 3 or 1,000 electron volt. We call that KeV. The kinetic energy of the electron is proportional to KVB, or the peak kilo voltage. So whenever we use higher KV, that means higher kinetic energy for the electron. So, for example, energies of electron accelerated by potential difference of 20 and 100 kV are 20 and 100 kV respectively. So if we use, in other words, if we use 100 kV, that means the energy of the electrons will be 100 kV. So when the electrons are attracted by the anode, by the target, there will be coulomatic Coulomb interaction because the electron is negative in charge. It will interact with the positive nucleus, and it will attract the electron, affect the direction of the electron and also the speed. So as a result of that, the speed of electron will be reduced, and as a result, Bremen-Stahling radiation is produced at the target. So the deceleration of an incident electron occur in the proximity of the target atom nucleus, because of the law of physics, the energy lost by the electron will be gained by the electromagnetic photon or the Bremsstrahlung radiation. The relation of the Coulomb force of attraction varies strongly with the distance, the inverse of the distance. The X-ray that are produced by the converging of the incident electron into electromagnetic radiation is known as Bremsstrahlung radiation, or the in Germany, the braking radiation. This is a diagram that shows the how the Bremsstrahlung radiation process. We have an incident electron. The distance between the electron and the nucleus, we call it the impact parameter, the distance, d. When the electron come close to the nucleus, it will decelerate and Bremsstrahlung radiation are reduced. And we call it the Bremsstrahlung radiation the radiated X-rays. So the relation 1 over square of distance. The impact parameter is the closest distance between the electron and the anode, the nucleus, will determine the amount of energy lost by the incident electron. So as the distance decreases, the amount of energy lost by the incident electron increase and the photon energy increase. When the direct impact on the nucleus, which is a rare event, when the electron directly hit the nucleus, this will be the maximum X-ray energy, or the Emax. So here there are 3 scenarios. The first scenario, when the electron will hit the nucleus, or the D will be 0 here. This is the maximum energy for the Bremsstrahlung radiation. The medium distance will produce a moderate energy. And the third scenario, when the distance is very high from the nucleus, we will have the low energy Bremsstrahlung radiation. So the distance will affect the energy of the Bremsstrahlung radiation. For that reason, the energies for the Bremsstrahlung radiation are continuous. So they are not discrete. They can have any way between the maximum energy and below. So it has a continuous spectrum of energy. We call that polychromatic spectrum, which means we have different energies of the photons. If we compare it to monoenergetic, monoenergetic means the same energy, but for here it's polychromatic, so it has the meaning is that we have different spectrum of energies for the Bremsstrahlung radiation. Usually, around the X-ray tube there will be filtration, the envelope of the X-ray tube. So this very low X-ray or very low Bremsstrahlung radiation will be absorbed by the filter. So only high energy X-ray will penetrate and reach the patient. So this we call it the Brimstein spectrum. Is the diagram that show you the energy of the Brimstein radiation and the relative output. So as you can see here, we have continuous energy spectrum. This is the theoretical and filtered Brimstein radiation. But in reality, as we said, since there are filtration, the low energy photons will not will be absorbed. So we are left only with the relatively higher photons, and the maximum energy is the maximum energy, where, as we said, at distance d. So this is an example of a 90 kV. You set the kV to 90. You will expect that the maximum energy will be 90 kE. And of course, you will have a spectrum of energies lower than the maximum energy. Usually, the average energy is about 1/3 to 1/2 of the kVb. This is the calculated average energy of the beam. So for the Brimstein radiation, the unfiltered energy spectrum is polychromatic. It contains a large number of very low energy photons. The spectrum approximately linear as photon energy increases. Due to the higher probability of a large impact parameter distance, the peak voltage applied across the electrode of the X-ray tube determines the highest energy, Emax. The lowest energy of the filtered X-ray is not easily determined due to, as we said, the filtration, severe attenuation of these photons by the material and the thickness of the X-ray tube envelope. So all diagnostic X-ray equipment, they have filters. They will remove, it is important to remove the low energy X-rays. The average energy, as we said, is about 1/3 to 1/2 of the Emax. So the X-ray production efficiency is influenced by the target atomic number and the kVb. The efficiency of the X-ray production efficiency is defined as the Emax multiplied by the Z number, 10 to the power -6. So it is defined as the ratio of the radiated energy or the Brimstein radiation loss to the collisional energy loss, excitation, and ionization. For example, at 100 kV, use the formula for tungsten. The X-ray production is 0.7. At 6 MeV or 6,000 keV, this is the therapeutic machine. Also using tungsten, the X-ray production is 44%. So as you can see here at the diagnostic level, energy or KVB levels. Only a very small amount will be production of Bremsstrahlung radiation or X-ray production. But for therapeutic, if you increase the KV to very high, mega level, the production of X-ray is increased. So most of the production interaction is heat. Excessive heat become less of a problem at higher energies. So we talked about the Bremsstrahlung radiation. Now we talk about the other type of X-ray produced, which is the characteristic X-ray spectrum. We will go back to the K-shell diagram. Will explain to us how the characteristic spectrum or radiation is produced. So recall that the orbital energy, electron binding energy, depend on the Z number. Whenever the Z number increase, the binding energy also increase. For an electron incident on a target exceed the target atom binding energy, it is possible for the collisional interaction to eject the bound electron and ionize the atom. So this is for the hydrogen, and this is for tungsten. For tungsten, for the K-shell, 69.5 electron volt. If the electron has higher energy than the K-shell threshold, then the electron can be ejected, and the atom is ionized. This is another diagram. It is easier to understand. So imagine this is one of the atom in the target, tungsten target, for example, and this is the incident electron. So the incident electron will interact with this inner shell electron and will force it to be ejected. Has enough energy that exceed the binding energy of the electron in that shell, which is the K shell. So what will happen? The result will be a hole. When the electron is ejected, there will be a hole. This hole will be filled usually by another electron from higher orbits. And when the electron fill that hole and a photon is ejected, an X-ray photon, which we call the characteristic X-ray. And the energy of that characteristic X-ray is the binding energy difference between the K shell and the L shell, which is unique. So if we go back to the previous slides, as you can see here, for tungsten, the K shell and the L shell, if you subtract the energy from the two shells, you will have a discrete energy which is discrete for tungsten. So the characteristic X-ray is only depend on the type of target you are using. So an outer shell will electron with lesser binding energy fill inner shell vacancy, As the electron transition to a lower energy state, the excess energy can be released as characteristic X-ray photon, as we said, with energy equal to the difference between the binding energy of the electron shells. So the binding energy are unique to a given element. The emitted X-ray have discrete energies characteristic of that element. So if we return to the spectrum for the certain X-ray beam, you will see that this is the Bremsstrahlung spectrum, which is continuous, and the characteristic spectrum is embossed on that. So we will have a complete spectrum for the X-ray beam. So the characteristic X-rays are shown as discrete energy lines on the continuous Bremsstrahlung spectrum. Example, at 90 degrees, 90 kV potential difference for tungsten. As you can see here, there are about 4 discrete energy levels for this characteristic photons for tungsten. So if you look to the spectrum of the X-ray beam, you will know what type of target based on the energy of the characteristic X-ray. This is another demonstration. We have an incident electron. That has binding energy higher than the binding energy of the shell. It will an electron will be ejected. Now, if that hole is filled by adjacent shell, we call that alpha, K alpha X-ray emitted. If the other scenario, if the hole is filled by non-adjacent shell, there will be a bigger difference. So the characteristic X-ray will be of a higher energy. We call that beta, K beta X-ray. This table will give you about compare different target. Tungsten, for example, molybdenum and rhodium. The K shell for tungsten 69.5 electron volt, kilo electron volt. Also the L shell and M. If you compare that with molybdenum, you can see that the characteristic X-ray is lower for molybdenum than the tungsten because of the different binding energies. So for tungsten, it is used general radiography. Molybdenum and rhodium is used for mammography units. So characteristic X-ray other than those generated through the K shell are not important because they are of lower energy. So they are not important in diagnostic imaging. Other transitions, characteristic X-ray energy almost entirely attenuated by the X-ray tube window or added filtration. Only higher energy photons can penetrate the X-ray tube. The K-shell characteristic X-ray only occur if the kinetic energy of the incident electron is greater than the binding energy of the electrons in the K-shell. For example, for the tungsten 69.5. So if the energy of the incident electron higher than 69.5, then we will have characteristic emission. As the energy of the incident electron increases above the threshold for characteristic X-ray production, the percentage of characteristic X-ray emission will increase. For example, for tungsten at 80 kVb, if you are using 80 kVb, 5% will be characteristic emission. At 100, there will be 10% will be characteristic compared to Bremsteining radiation. So increasing the voltage will increase the production of characteristic radiation. So we talked about the two type of X-ray radiation produced, the Bremsteining and the characteristic X-rays. But for the parameters that we are using for the X-ray unit, we have the potential difference, kVb, and the tube current in MA, and the exposure time in seconds. These are the selectable parameters to determine the X-ray spectrum characteristics, quality, and quantity of the X-ray photon. Now we go back to the X-ray tube. We talked about the cathode, and we said that the cathode is the source of electrons, the anode, the target. Also, as you can see here, usually the anode is rotating. This is the anode rotor, and this is the stator. The stator is the fixed part. The rotor is the moving part or rotating part. It is rotated by the by induction, by applying magnetic field. So you don't have to go in details of electrical engineering, but we'll have only just important information for us. Also, as you can see here, the tube housing, the lead shielding surrounded the X-ray tube will reduce the radiation around the X-ray tube. The lead shielding will reduce the leakage radiation to 100 milliampere per hour at 1 meter from the X-ray tube. Also, there are oil, as you can see here, to absorb the heat, to control the heat of the X-ray tube. So protecting housing of the X-ray tube will reduce the intensity of leakage radiation to less than 100 mR per hour at 1 meter. Now, actually, this is the manufacturer of the X-ray tube rule is to make sure that the X-ray tube will not exceed, the leakage of radiation will not exceed the limit, so that staff around, operator around the X-ray unit will not receive more radiation because of working with X-ray units. Now we go go inside the X-ray tube itself, and we go to the cathode, for example. We said that the cathode is the source. The role of the cathode is to produce electrons, where the electrons then are accelerated by the voltage. This is how the X-ray tube look like. Helical tungsten wire filament. You have two here. There are traces of thorium to prolong the filament life and increase electron emission efficiency. The filament is surrounded by a focusing, they call it a focusing cup. It is around 10 volt, 7 ampere circuit. The electrical resistant heats the filament and release the electrons through thermionic emission. They produce an electron cloud. The filament current adjustment control the tube current, or the rate of electron flow from the cathode to the anode. So the filament current will affect the tube current. The focusing cup rule is it's made of metal that surround the filament. Electrons are accelerated from the cathode to anode. They usually spread without using the focusing cup. They will spread out because of repulsion. So using the focusing cup, it will hit the anode. We make sure that it only hit the anode or the target. The focusing cup width determine what we call the focal spot width. The filament length also determine the focal spot length. We have small and large focal spot filaments. Usually for diagnostic, we have two spot sizes. Now we talk about the anode. The anode should be made of high melting point to sustain the heat. It should be of high atomic number in order to increase the Bremsstrahlung production. Tungsten usually is the preferred type of target because it has a high Z number. Also, it is enriched with uranium for the heat, to sustain heat. For mammography, we use molybdenum, which is suitable for mammo, as we will see, we'll talk about later. But for general X-ray, we use tungsten. Usually, as we said, that the anode is rotating to dissipate heat, but there are also fixed anode or not rotating anode. In that case, for dental or portable C-armed fixed anode are used. The advantage of rotating anode for better heat dissipation. Also, we talked about the rotating anode. We said that is by induction, by the magnet. The magnet is formed and rotates the anode. Also, the rotor is equipped with heat features. The anode cools through radiative emission, heat transfer to oil, bath of the tube, and so. The induction motor, when the radiologic technologist push the exposure button of the radiographic system, there is you will notice a short delay before an exposure is made. The reason for that, this will allow the rotor to accelerate to the designated round per minute while the filament is heated. Then only the kV applied at that time the kV applied to the X-ray tube. That's why you notice a short delay between when you press the button, so that the rotor will reach the speed needed for before the kV is applied. Now we talk about the angle of the anode and the focal spot. You will notice also that we said that the anode is rotating to dissipate heat. Also, you notice that the surface of the anode has an angle. This angle is important so that the electron will hit a larger area, and the focal spot, the apparent focal spot, will be by this geometry will be smaller in size. So this geometry will dissipate heat better, and will have an effective lower or smaller focal spot. The effective focal spot length is less than the actual focal spot length. This we call it the line focus geometry. Or the line focus principle. The effective focal spot size equal the length of the width of the focal spot projecting along the central axis of the X-ray field. It is a parameter of the angle. The reason for smaller focal spot will improve the spatial resolution. So we'll have sharper images when we are using small focal spots. Also, the Hill effect, we will talk about the Hill effect. The reason for the Hill effect, some of the X-ray produced are absorbed by the anode itself. So the intensity of the X-ray beam produced will be less of intensity to the anode side as compared to the cathode side. So we'll have more radiation along the cathode side compared to the intensity along the anode side. This we call the Hill effect. And as we said, there is a self-filtration by the anode. There are advantages for the Hill effect. For the PA chest exposure, we orient the chest to the anode and the abdomen to the cathode to compensate for the tissue difference. For mammo, also, we orient the nipple side to the anode and the chest wall to the cathode in order to compensate for the anatomy. The Hill effect is not that important. We are using large SI distance or source to image receptor distance. So at high SID, the Hill effect is not that important. Usually, the cathode anode direction and the focal spot are indicated on the X-ray tube housing. Direction is clear. There is a label that shows you the cathode anode direction and also the focal spot size. We talked about filtration. We said that filtration will attenuate the X-ray as it passes through the layer of material. There are inherent filtration and added filtration. The inherent filtration are built in the X-ray tube. It is the glass or metal insert at the X-ray tube. Attenuate energies less than 15 kV, and also there are added filtration. The added filtration are sheets of metal, usually copper, of a copper material in the X-ray tube housing. They, as we said, the rule of the filtration is to absorb low energy X-rays in order to reduce the patient dose, since low energy X-ray are absorbed by the skin of the patient, and they don't contribute to the image, so they only increase the dose. So the added filtration will reduce the patient dose and also will increase the beam quality, so that most of the photons are penetrating photons that will contribute to the image. We talked about the half value layer in unit of millimeter of aluminum. They are, if you measure the half value layer, it will give you a measure of the effective energy of the X-ray beam. That's why regulation requires that the half value layer is measured and calculated every year, so that they are according to the standards. So this diagram will show you the effect of filtration. If you compare filtered beam with unfiltered beam, as you can see here, most of the photons are of low energy that will not contribute to the image, but it will increase the dose to the patient. Filtration we will have only higher photons energy, which is important for the image quality. Now we talk about collimation in the X-ray tube. The collimation will adjust the size and the shape of the X-ray beam. The collimation are of parallel and opposed lead shutters. They are made of lead. Lead has an ability to absorb photons. And usually there is a light comes from the X-ray tube that that will show you the territory of the radiation, and the light field should comply with the actual radiation, and according to the regulation, there should be the error should be limited, so that the light represent the actual radiation. This is a diagram that show you the difference between good collimation and poor collimation. This is a properly collimated beam, and this is, as you can see here, improperly collimated beam. The collimation will reduce the dose to the patient as low as reasonably achievable. To comply with the ALARA principle. The limited radiated field will reduce scattered radiation. So in this case, you see there are scattered radiation that will not be detected by the image receptor. And improve the image contrast. Some of the units are equipped with positive beam limitation, which means that the X-ray unit itself will have auto beam collimation, will automatically define the proper collimation. Now, on the operator console, the technologist will select the peak voltage, the tube current, and the exposure time, and the focal spot size. The KV determines the X-ray beam quality, as we said. The higher quality, the penetration of the beam or the average energy is important to improve the subject contrast. Also, you will choose the X-ray tube current in A, which will determine the X-ray fluence rate, photon per cm square per second emitted by the X-ray tube at a given kVb. The mass or the product of the current, the tube current, and the exposure time is proportional to the fluence rate. Whenever we increase the mass, that means more fluence rate more photons are produced. Low MA selection will allow the small focal spot size to be used, and higher MA require the use of larger focal spot due to the anode heating consideration. So we cannot use the small focal spot frequently. If we have higher patient load, then we need to use the larger focal spot, which sustain heat more than the small focal spot. Now we talk about the X-ray generators, the circuit design. We have single and three-phase generators. The single-phase generator results in a pulsating beam, alternate swing in voltage, will produce low-energy X-rays. The new type is the three-phase generator, three single-phase waveform out of phase by 120 degrees, is nearly constant voltage, higher effective energy, greater control over exposure time. The voltage ripple or the percentage voltage ripple, the subtraction of V max minus V minimum over V max times 100%. So for a single phase, as you can see here, the maximum the voltage go to maximum and then go to zero again. So the voltage ripple is 100. For single phase, 2 pulses, also the same because the voltage alternate between maximum and zero. But for three phase, the voltage ripple is lower, and we have constant, almost constant voltage until high frequency voltage ripple produce nearly constant voltage. So nearly all mammography and CT spiral system, they use high frequency circuits. So the less the voltage ripple factor will result in greater radiation quantity and greater radiation quality. What are the factors that affect the X-ray emission, the quality and quantity? For quantity, the number, we mean the quantity, the number of X-ray in the beam. They are proportional to the Z number, the square of the KV, KVB, and linearly with the mass. So as the mass increase, also the linearly the quantity or the number increases. The quality is the quality of the beam or the penetration of the X-ray beam will depend on the KV, the KVB, the generator waveform, and the tube filtration. So as you can see here, whenever the energy increases, also the output increases, and the maximum energy also increases. Here you see how the voltage ripple, the type of generator you are using, will affect also the energy spectrum, and also the the photon fluence. The exposure will depend on both the quantity and quality. Changes in the kV can be compensated by the changes in the mass. So you can use this formula. If we, for example, if we go to higher energy, we can lower the mass to have the same exposure. Example, if we change from 60 kV to 80 kV, using the formula, the dose will increase by 78%. So increasing the kV will increase the dose or the exposure. Now, if we lower the mass using the higher energy, the higher kV, for example, we are using 40 mass with 60, and we increase the kV to 80. Using the formula, you can find that lowering the mass to 9.5 will give you the same dose or the same exposure if you use a higher kV. And this will show you how that the exposure is affected by both by the kV and also the mass. Actually, in new or modern units, you don't have to calculate because we have what we call the automatic exposure control, the AEC. The AEC will choose for you the right kV, the right MA, or the mass that will give you the better image quality and better parameters using the AEC. So although the technologists can manually time the X-ray exposure, he set the MA exposure of the mass. The photo timers help to provide a consistent exposure to the image receptor. So usually the photo timers, or sometimes we call them AEC detectors, are in the detector itself. The photo timers will measure the actual amount of radiation incident on the image receptor and terminate the X-ray production when the proper radiation exposure is obtained. Compensation for the patient thickness and other variation attenuation are achieved at the point of imaging. Usually, a phototimer system consists of one or more detectors. For general radiography, usually there are 3 AEC detectors, 1 central and 2 lateral phototimers. So we are finished with the X-ray production and X-ray output. Now we move to the projection imaging presentation. Okay, in this presentation, we'll talk about projection radiography. Projection imaging usually in a X-ray unit. You can see here that the X-ray tube itself. You have the image receptor, the body, and also the wall body or the chest body. Here, the X-ray radiation, the X-ray source is outside the patient, will radiate the patient as an external source. And we call that projection imaging. In nuclear medicine, for example, the patient is injected with radioactive material. So the radiation, the patient himself is the source of radiation. And we call that nuclear imaging. But for the projection imaging, the source of radiation is outside, and the distance between the focal spot and the detector itself, we call it the SID, the source to image receptor distance. The distance between the source, the focal spot, and the patient, we call it SOD, source to object distance, and the object to image receptor distance, OID. So usually the screen film are put here under the patient table, and after that the film is developed, and where the optical density will show the details of the image. So projection imaging, we have an acquisition of 2D image of the patient who is a three-dimensional anatomy. The X-ray source is outside and irradiates the patient, and due to the attenuation through the difference in the attenuation will have different optical density, and the image is formed. The optical density is a measure of film darkening at any location on the film, correspond to the attenuation characteristics of the patient at that location. If we assume that the source of radiation is a point, then we can use the geometry or the trigonometry using similar triangles, and we can easily use the geometry principles to find any distance we want. But usually the actual scenario is that the focal spot, if it has a finite size, and not actually assuming that is a point source is approximation that we can assume in order to apply the geometry principle. Similar triangles are encountered during image magnification and when evaluating image and sharpness caused by focal spot size and patient motion. Magnification usually occur because the X-ray beam diverge from the focal spot to the image plane. So the definition of magnification is we can measure the or divide the image on the image receptor compared to the object. And this is the definition of the magnification. And by applying geometry principles, it is equal to the SID over the SOD, which is the source to object distance. Magnification is largest when the SOD is small. So if this denominator is small, we will have the highest magnification. In other words, when the patient is near the tube, we will have the higher magnification. So this is when we assume that the source of radiation is a point source, which is not true. Actually, the source of radiation is the focal spot, and it has a finite size. So we will use another type of geometry that will, as we can see, we will have a blurring in the image. So we will try to calculate the blur and find the relation between the blur and the image and the focal spot size. So the blur, or they call it penumbra also. Here the F, we can use the geometry principles to calculate the blur in terms of the focal spot, and find that the blur will depend on the size of the focal spot and also the magnification. So the blur will increase with the focal spot size and also the magnification. The smaller the focal spot size, we will have a less blur. So we have two scenarios here. We have small focal spot and large focal spot. As you can see here, using smaller size focal spot, we'll have less blurring. But if you use a large focal spot, we have a wider blurring. So the less the blur effect, and the better the resolution in the image with smaller focal spot. However, a small focal spot cannot sustain high tube currents, which are required for short exposure times that are useful in reducing the patient motion artifact. This is due to its inability to dissipate the heat rapidly enough as compared to the large focal spot. Typically, we have an X-ray tube with dual or triple focal spots, so that the best performance for the procedure can be used. Balancing heat loading of the focal spot with the requirements for resolution and magnification. So we have two images here, one with the small focal spot and the one with the large. And as you can see here, the one with small focal spot is sharper than the other one. You can see here the blurring. Even the blurring is higher with magnification, as you can see here, as compared to the small focal spot. So in real imaging situation, the size of this the focal spot is the limiting factor to the amount of magnification that can be used. So with the magnification, as you can see here, we have more blurring and sharpness, and this is the limiting factor. The size of this focal spot will affect the degree of magnification you can have with a good image quality. Also, we talk about the inverse square law in projection imaging, how it's affect the effect of the inverse square law. So the inverse square law states simply that the number of X-ray striking an area, the intensity is inversely related to the square of the distance from the source. So we assume the I is the intensity at the point, and D is the distance from the source. As the distance from the source increases, the beam diverges, so that the constant number of photons being produced at the focal spot is distributed over larger areas. This will there will be fewer X-ray reaching any given spot on the detector, resulting in an overall increase in the noise within the image. So in order to compensate for this effect, more X-rays would need to be produced as the distance increase in order to maintain the mean number of X-ray photon per unit area at the same level as at closer positions. Now, if we talk about the source to object distance, as the source to object distance increase, it causes the X-ray beam to appear to come from smaller focal spots, yielding a sharper image from less focal spot blur. However, the inverse square law has an effect as the SOD increase and must be compensated by increasing the tube current for more X-ray output. On the other hand, a shorter SOD will yield more X-ray and reduce the noise, but at the expense of decreased sharpness due to the increased blurring from the focal spot. Now, if we concentrate on the object to detector distance, or the ODD, as the object to detector or image receptor increases, it will introduce magnification, yielding better effective spatial resolution at the image receptor at the cost of more blur due to the increasing effect of focal spot size. As the ODD is decreased, the magnification go down, but so does the focal spot flare effect. So the image is sharper. If we compare between the KV and the entrance skin exposure, if we measure the exposure at the entrance to the patient's skin and draw a table, as you can see here, as the KV increase, the entrance skin exposure decrease. So lower KV or less filtration provide less X-ray penetration and less scattered radiation, leading to higher contrast. However, technique using softer beam further require more photon in order to penetrate the body part, as these photons are also more highly absorbed by the body, so the patient dose will be greater. On the other hand, higher KV beam or more filtration provide more X-ray penetration and more scattered radiation. This will lead to lower contrast, but also lower dose. So for a given body part, the selection of proper beam energy requires a careful balance between the needed contrast and the patient dose. So increasing the KV will lower the dose to the patient, but will lower the contrast. So we need to make a balance between the contrast and the patient dose. Here a comparison between a lower KV and high KV. So you can see here the contrast is high, is better for the lower KV. This will show you the effect of increasing the KV on the image quality. So increasing the KV will have a lower contrast. Now, what about scattered radiation? When the X-ray beam interact with the patient, a scattered radiation will be also produced. The scattered radiation will affect the image quality, will lower the image quality on the image receptor. So we need to get rid of or reduce the scattered radiation. So scattered radiation will violate the basic principles of projection radiography. That is, projection radiography assume that the photons travel in straight line from the X-ray source or the focal spot to the image receptor. The scattered photon, if detected by the film, will cause film darkening, but provide no useful information on the image. Usually, the scattered photons is a result of the Compton interaction within the body. The result of Compton interaction is redirected lower energy photon. That's why we need to use what we call the anti-scatter grid. The anti-scatter grid is used to clean up scattered radiation. It is placed between the object and the detector. It uses geometry to lower the scatter radiation. So it's usually made from lead and also other lower material like aluminum and carbon fiber aligned with the focal spot. The grid ratio is defined as the H over W, or the septa height, and the interspace width of the grid. So for each grid, there is a grid ratio. As the grid ratio increases, also the dose to the patient increase. Grids come in a large variety of sizes, shapes, and grid ratio. A linear grid is the most commonly used design. The lead strips are linear in nature and are aligned with the X-ray tube anode to cathode axis. As the grid ratio increases, the number of scattered X-ray absorbed by the grid increases, and the presence of scattered X-ray, percent of scattered X-ray transmission reaching the receptor decreases, and the image contrast improves. However, as the grid ratio increases, the dose also to the patient will increase also. There are other types than the linear. We have what we call cellular grids used in some mammography systems. You can see how they improve the image quality. This will compare the grid ratio for different modalities. So the cellular grids used in mammography, the X-ray focal spot must be maintained at a specific distance from the grid. Usually, using grid, there are some artifacts due to the mispositioning of the grid. So, as you can see here, this is the correct setup. Sometimes it is used upside down, or different angle through, or sometimes off center. All these or off focus will affect will result in image artifacts. That's why the grid need to be positioned correctly. So as we said, as you increase the grid ratio, the cleanup of scatter striking the grid at larger angle, more cleanup at a larger angle, but it is less effective for smaller angles. Also, the grids are, we have a grid frequency, which is the number of line per cm. will not affect the grid frequency will not alter the percentage of scatter to primary radiation. Also, we have stationary grids and moving or putty grids. The bucky is a device that moves the grid during the exposure. Since the grid lines could cause artifacts when digitizing the film, as you can see, the bucky using a bucky a grid is better than the stationary one in the image quality. Also, here we define the bucky factor, which is the dose with the grid over the dose compared to the dose without the grid. So this will give you indication of the dose increase due using the grid. It's usually between 2 to 3 the range of the increase in the dose when using the grid. So you can compare here no grid and using the grid also. Some artifacts when are not using the grid properly would affect the image quality. Now there are other way of reducing the scatter without using the grid. We call it the air gap technique. The air gap will lower the scattered radiation and increase the magnification and also will improve the image quality. It is usually used in chest radiography, also in mammography. There is you keep a distance between the detector and the patient. This will leave the scattered radiation not detected by the detector itself, as you compare to the if you keep the detector close to the patient compared to the air gap technique. You can see there is some of the scattered radiation will go away from the image detector without interaction. So the air gap technique will improve the image quality by lowering the scattered radiation. And as we said, that it's used in chest radiography and mammography. So we are finished with the projection imaging. We will have a 10-minute break and we'll be back at 11:20. Okay, our next session will be graphics question review about the presentation we took today. The first question is about tungsten has the following binding energy: K shell 69 kV, L is 12 kV, and N is 2 kV. 68 electron striking a tungsten target could cause emission of which of the following photon? 66 kV characteristic, 57 Primstalin, 57 characteristic, and 10 keV characteristic X-ray. And here you give you A, B, C, D, different type of answers. So before we analyze this question, first we need to remember that the electron striking the tungsten is 68 kV, and we need to compare that to the K shell. The K shell is 69 kV, so the electron is less than the K shell energy, so it will not dislodge the electron of the K shell. So in this case, we will not have because the energy of the electron is less than the K shell, we will not have an ejected electron. So we are left now with the Primstalin radiation, which will depend on the. We know that it has a spectrum of energy, so the Primstalin is a true. We will have it with one of the photons. Now, since the electron, the K shell is not one of the possibilities, then we have the other possibility, the M shell and the L shell. So if you subtract 12 from 2, you'll have 10 keV. So 10 keV characteristic is a possibility. So only 2 and 4 are the possible answers. And in that case, answer C is the correct answer. The other question is in the figure below. This is a spectrum of a beam. We have 3 X-ray spectra from same target material. Answer A for true and B for false. So curve A is hypothetical, a pure X-ray spectrum produced at the target surface without attenuation of filtration, which is true. We mentioned that this is the hypothetical curve without filtration. Curve C represent more penetrating X-ray beam than in B. Usually, we define the average energy as the 1/2 or 1/3 of the maximum. So the average energy for C is higher, as you can see here, is higher than B, which means that curve C is higher in energy than an average energy than B. So curve C is more penetrating than B, which is 4. Nine, the maximum energy in curve B is about 33. That's false. Curve B, the average or the maximum is, as you can see, 100. So that is false. 33 is false. Number 10, the energy of the characteristic X-ray in curve C is higher than that in the curve B. Actually, as you can see here, the characteristic emissions are all the same, since we are talking about the same target material. So it is the same for both, which means that the statement is false. The target material, number 11, the target material for the 3 spectra could be molybdenum. Well, molybdenum is of lower energy, so this is a higher energy. So it's a false statement. It's not molybdenum. Actually, the characteristic radiation for moly is 16 and 19. So this is, we can say it is tangent on the characteristic energies. Question 3, in comparison to 20 kiloelectron photons, the probability of photoelectric interaction in bone at 60 is approximately 27 times as great, 3 times as great, the same, 3 times less, or 27 times less. So in the second presentation, we talked about the probability for photoelectric interaction, which is proportional to the Z cube over energy cube. If we just use the energy, we compare the 60 to 20, and the energy and the Z number. So for the energy, 20 over 60 to the power 3, 1 over 3, so 1 over 27. So answer E is correct, 27 times less. Because as we increase the energy, the probability for the photoelectric effect decreases. So the answer for that is E. Question 4, electrons lose energy when passing through matter by the production of beam-Strahling, photoelectric interaction, collision with other electrons, production of delta rays. First of all, electrons are charged particles, and we know that charged particles, they are, if you remember, they interact by 3 interactions: excitation, ionization, or beam-Strahling. The production of Primistahling is true. The photoelectric is for photons, so it is false. Collision with other electrons, which could be a possibility. And also the delta rays is also a possibility. So the correct answer are 1 and 3 and 4. The delta rays due to secondary radiation, so the electrons can produce also secondary radiation. Which is a characteristic of photon interaction with soft tissue. So he's giving you here some Compton, some pair photoelectric, and no pair production. Some Compton, some pair production, no photoelectric. Actually, photons interaction, we know that photoelectric is one of the type of interaction, and also Compton, and coherent scattering, and also pair production. But the pair production, we said that it's only for higher energies. Primistahling is for the interaction between charged particles with matter. The correct answer is A. Some Compton, some photoelectric, and no pair production. In Compton interaction, the primary X-ray will interact with an outer electron, resulting in ejected electron plus positron, ejected electron plus characteristic X-ray, recoil electron and photon of less energy, the convergent electron plus photon of less energy, or Auger electron plus photon of less energy. First of all, you can exclude the characteristic X-ray, because the characteristic X-ray is for the interaction. We know that for the photoelectric effect, not for the Compton. So positron also is not true. C, recoil electron and photon of less energy, which is the right answer. The Compton is a recoil electron and photon of less. Actually, the photon will lose some of its energy and will change direction. So the right answer is C. The ratio of heat to X-ray produced in a typical diagnostic target is 1 to 99, 10 to 90, 50, 50, 90, 10, or 99 to 1. If you remember the presentation about the X-ray output, the answer was 99 to 1, which is E. 99 of the interaction will be in the form of heat. So the answer is E. Atomic shells with the principal quantum number n equal 1, 2, 3 are traditionally referred to as what the letters are used or the numbers. If you remember the presentation about the first one about the atom and radiation, the answer is B, K and L and F, or we call them the K shell or L or M shell. This is a little bit difficult question, but it will give you a clear understanding how the interaction between the different K shells. So consider an atom with the following binding energy: K shell 30, the M shell 0.7. And the L shell is unknown. An electron with a kinetic energy of 25.3 keV is ejected from the M shell as an auger electron following L to K shell transition. Then what is the binding energy of the L shell electron? Remember that when we talk about the characteristic X-ray, when there is a vacancy, here we can see there is a vacancy in the K shell, and an electron will fulfill that vacancy from the L shell. Usually a characteristic X-ray is ejected. But in some cases, instead of the characteristic X-ray, we have an auger electron is ejected in order to conserve the energy, the physics law. An electron called auger electron is ejected. So we assume that is the same actually as the scenario of the characteristic X-ray. The energy of the electron will be the energy between the two K shells plus the binding energy of the K shell. So the energy of the kinetic energy of the electron, 25.3, plus the binding energy from the M shell will equal 26 keV, where E is equal to the difference between the binding energy of the K and the L shells. So we put that in the formula. The binding energy of the K shell minus the binding energy of the L shell, the difference between the two, and will be about 4. So 30 minus 26 is 4. So the answer for that is B. So this is how we calculate the binding energy as example of auger electron. It is similar to characteristic X-ray. Two filaments are found in some X-ray tubes. The purpose, this is a good question actually. why we have two filaments, small filament and large filament. A function as a spare in case of one filament burn out. Reduce higher tube currents by using both filaments simultaneously. Double the number of heat units that the target can accept. Enable the smallest focal spot to be used consistent with the KVMA setting. Well, the right answer is the last one is B. It will enable the smallest focal spot to be used consistent with the KVMA settings. All of the following affect the shape of the X-ray spectrum except the added filtration, the type of rectification used in the X-ray circuit, the speed of rotation of the anode, the energy of the electron hitting the target, the composition of the X-ray target. Actually, all of them are true, are affecting the shape, except the rotation, the speed of rotation of the anode. So the answer is C. The quality of an X-ray beam cannot be characterized only in terms of the KV because beams with the same KV may have different filtration, different value layer, maximum wavelength, target materials, all of the above. Actually, all these are will affect the KV. We have the same KV with different. This will affect the quality of an X-ray beam. Filtration will affect the quality, the half value layer, the maximum wavelength, the target material. So all of the above is the right answer. In an X-ray machine with a tungsten target, increasing the KV from 100 to 125 will increase all of the following except the total number of X-ray emitted, the maximum energy of the X-rays, the average energy of the spectrum, the energy of the characteristic X-ray, the heat unit generated for the same mass. The answer for that is the energy of the characteristic X-ray, because we know that the energy of the characteristic X-ray is affected only by the type of target material. So the answer is D. At 90 keV photon beam, 90 keV photon beam interact with an atom whose K-shell binding energy is 5 keV. An electron is emitted with a kinetic energy of 85. Which of the following is false? Characteristic radiation will be emitted. 90 keV photon disappear. The electron will be absorbed within 1 cm of its origin in tissue. This is example of a Compton scattering. Actually, this is example of photoelectric absorption since the product is 85. So 90 minus 5 is 85. So this is example of characteristic of photoelectric photoelectric absorption. So the only false statement is the example of Compton, which is not true. Which of the following does not improve the heat capacity of the X-ray tube? The rotating anode, the small target angle, the large focal spot, thermionic emission, none of the above. Well, the heat capacity, we know that it's related to the rotating anode. And the target also, the small target angle, the large focal spot compared to the small focal spot. So the answer is the thermionic emission, which is the emission of electron from the heated cathode. For a fixed spot size, using smaller target angle increase the incident area of the electron on the target and will have an effect on the heat capacity. The effective energy of an X-ray beam linearly increases with the Z number proportional to the mass, is not affected by the added filtration, is equal to the KVB, affect subject contrast. Actually, the answer is E. The effective energy of an X-ray will affect the subject contrast, and none of the statements are true from A to D. Is not the effective energy is not equal to the KV. What is equal to the KVB is the maximum energy and not the effective energy. So the answer is E. With that, this is the last session we have. So we finished early this today. Inshallah, we will meet tomorrow at 8 o'clock. Inshallah. Thank you.